Every glass substrate, BOE, produces roots through a laser that fires at a precision of a few microns, and that laser does not come from China. The glass is Chinese. The tool that makes the glass usable is not. The question this map follows: can BOE build a complete supply path for glass substrate advanced packaging before the companies that own those tool nodes decide to close the line? A breakthrough in materials is not a breakthrough in the network. BOE producing a glass substrate at scale changes the shape of one node on the map, the substrate node, but the lines that run into and out of that node still pass through tool and metrology choke points that sit outside China's current reach. The story of glass substrate chips is not about the glass. It is about whether the rest of the web can be redrawn around it. The physical unit this map follows is a single through glass via one blind hole, roughly 10 microns wide, drilled through a borosilicate panel. Everything that has to go right for advanced glass packaging to work passes through that hole. The laser that drills it, the metrology that confirms its depth and wall angle across a panel of thousands, the optical interconnect that will eventually pass a signal through it. The hole is small enough to be invisible. It is the junction the whole map converges on. The first line on the map runs from raw borosilicate sheet to a panel you can actually route signals through. That line passes through one critical tool, a laser system capable of drilling blind vias below 15 microns in diameter with a controlled taper and minimal cracking of the surrounding glass. The physics involved require an ultra-short pulse laser, typically operating in the picosecond or femtosecond range, where the pulse deposits energy faster than heat can diffuse outward. That keeps the glass from fracturing along the edge of the hole. Get the pulse duration wrong, get the beam profile wrong, and the via wall is rough, the taper is uneven, and the copper fill that follows it either fails to adhere or creates a void that becomes a reliability problem 3 layers up. The vendors who build these systems at packaging-grade specification are concentrated in a short list. Companies in the German photonics cluster and in Japan's industrial laser segment have developed these tools over decades of co-development with the display and semiconductor industries. Reports suggest Chinese laser tool development is active. Domestic vendors produce ultrafast laser systems for display cutting and solar scribing, and those applications require real precision. But the specification jump from display-grade drilling to through glass via drilling for advanced packaging is not incremental. Display cutting works at geometries measured in hundreds of microns. A 10-micron via with a controlled sidewall angle and sub-micron repeatability across 50,000 holes on a single panel is a different engineering object entirely. No Chinese vendor has publicly confirmed volume shipments of through glass via class laser tools to an advanced packaging line. Think of this tool as the single drill press at the center of a workshop. You can mill the wood, you can finish it, you can design the joint, but until the hole is in the right place at the right depth, nothing assembles. Every downstream step on BOE's glass substrate map routes back through that one press. Without a domestic press at the right specification, every panel BOE produces for packaging applications depends on a tool node it does not control. Node: through glass via laser drilling tool. Status: a choke point with no confirmed domestic bypass at the precision tier advanced packaging requires. Domestic laser capability exists at lower specification, but the gap between that capability and through glass via class drilling has not been publicly closed. Before following the next line, I want to mark something plainly. BOE's glass substrate is real progress at the materials node. The default reflex in Western commentary is to discount Chinese materials advances as incremental, and I think that reflex is wrong here. Getting a borosilicate panel to the quality and consistency required for advanced packaging is not a trivial achievement. What I am skeptical of is the slide from "the substrate node is controlled" to "the network is closed." Those are different claims, and the map does not support the second one yet. Controlling the substrate is controlling one node in a multi-node web. The lines into and out of that node are what this map is tracing. The second line runs from a drilled and filled via to a confirmed, stackable interconnect layer. Once the hole exists and copper has been deposited inside it, the process moves to building redistribution layers on top of the glass. Thin layers of dielectric and metal that route signals from the via to the next component in the stack. A modern glass interposer for high-density packaging might carry 20 or more of these layers. Each one has to land within a tolerance that narrows as the stack grows. The error budget shrinks with every layer added because misalignment accumulates. A slight drift in layer 2 compounds by layer 10, and by layer 20, you may have a via that was perfectly drilled but is no longer electrically connected to anything useful. The tool that closes this feedback loop is a metrology system capable of reading buried features through glass. It has to see a copper via under a dielectric layer, confirm that the next layer landed in alignment with it, and do this across the full area of a production panel at the speed required to keep the line running. Advanced overlay metrology and buried feature inspection tools for heterogeneous packaging are supplied by a tight cluster of companies. KLA, based in the United States, describes advanced packaging metrology as a growth segment in its own public disclosures. A small number of European and Japanese vendors occupy adjacent positions on this part of the map. China has domestic metrology development underway. Industry and Trade Reporting names this as a priority category within China's equipment programs. But independent benchmarks confirming that domestic tools meet the throughput and accuracy requirements of a 20-layer glass packaging stack are not publicly available as of mid-2025. A 20-layer glass stack without confirmed metrology is like building a suspension bridge by adding one cable at a time with no tension gauge. Each individual cable looks correct in isolation. The cumulative drift across all of them is only visible at the end, and by then, the failure is already in the structure. The metrology tool is the gauge. Without it, you do not know whether the stack you built matches the stack you designed until you test a finished device, at which point the cost of the error is already locked in. This is the segment where I revise my earlier hypothesis. I entered this map expecting the laser drilling tool to be the harder node. Having traced the metrology line, I now read it differently. A laser tool can be approximated at lower precision and improved iteratively. The physics of ultrafast ablation are well understood, and while the intellectual property is protected, the knowledge base is not as tightly concentrated as the most restricted tool categories in the semiconductor stack. A metrology tool that confirms buried layer alignment across a production panel at throughput is a harder engineering object. It has to be right in real time, not eventually. And the knowledge embedded in those tools is not only optical design. It is the accumulated process record of what a correct via looks like. In glass, at depth, with copper fill, under a subsequent dielectric layer, at every temperature and pressure variation the production environment introduces. That record was built over years of co-development with leading-edge packaging lines. You cannot replicate it by designing a new sensor head. Node: overlay and buried feature metrology for glass packaging stacks. Status: a choke point with a bypass route under construction. Domestic Chinese metrology development is documented and funded, but no confirmed volume-capable domestic tool at the 20-layer glass packaging specification has been independently benchmarked. The third line runs from a working glass substrate with confirmed vias and confirmed alignment to its highest value end use. Glass is not just an alternative to silicon or organic substrates for signal routing. It has optical properties that make it a candidate for co-packaged optics, where optical and electronic signals share the same package, and for micro-light emitting diode integration, where the glass becomes both the substrate and part of the optical path. This is where the through glass via becomes more than a signal route. The hole that the laser drilled and the metrology confirmed is now part of an optical coupling problem. A photon has to pass through or past it. The geometry that was sufficient for electrical routing has to meet a different set of tolerances for optical alignment. BOE has disclosed that it is building a team for this integration work. A team being staffed is a real point on the map. It is also an early stage point. The tools and process knowledge for coupling a laser diode or a micro-light emitting diode array to a waveguide in glass at package level are held by a different set of companies than those who make the substrate. Photonics integration equipment vendors, die bonding toolmakers, and the optical modeling software that predicts coupling loss at the junction between a semiconductor emitter and a glass waveguide. Several of those vendors are non-Chinese, and most of them have roadmaps tied to the broader co-packaged optics adoption curve being driven by data center interconnect demand. The glass substrate reaching co-packaged optics integration is like finishing the concrete foundation of a building and then realizing the plumbing, the electrical conduit, and the ventilation all require specialist contractors who are not yet on site. The foundation is real, and it matters, but the foundation is not the building, and each trade that has to enter the site is another line on the map that has to be traced to its source. Node, co-packaged optics and micro-light emitting diode integration tooling and process knowledge. Status: a choke point with no bypass currently mapped. BOE's team formation is the start of a line being drawn, not a routed bypass. The tool and process nodes for optical coupling and micro-LED bonding at packaging scale sit outside confirmed domestic supply. My hypothesis going into this map was that the laser drilling tool would be the true dead end. Having traced all three lines, I am marking a different node as the closest thing this map has to a permanent one: the metrology infrastructure that closes the feedback loop across a full glass packaging stack at production throughput. Here is how I hold both sides of that call. The case that this is a durable, possibly permanent, dead end. Overlay and buried feature metrology for heterogeneous glass packaging is not only a hardware problem, it is a hardware plus software plus process knowledge problem. The tool has to know what a correct via looks like in glass, at depth, with copper fill, under a subsequent dielectric layer, while the panel is moving through at production speed. That knowledge is embedded in the tool's algorithms as much as its optics. The companies that build these tools have accumulated that knowledge through decades of process co-development with leading-edge fabs. That record is not something you replicate by designing a new sensor head or by hiring engineers who once worked near one. Reports suggest China's domestic metrology programs are well-funded and technically serious. But the gap between a funded program and a tool that a production line will trust with a 20-layer stack is wide, and no public evidence has closed it. The case that a bypass is coming. China's semiconductor equipment investment is, by multiple industry and government reports, at a scale that signals this capability gap is treated as a national priority, not a research question. Metrology algorithms can be trained against domestic process data if the domestic process data exists at sufficient volume and variety. BOE's own glass substrate line, if it reaches meaningful production volume, becomes the training environment. A domestic metrology vendor co-developing with BOE on that line is a plausible path. Reports suggest this co-development model is already being attempted at other nodes in the Chinese equipment stack. The training data problem is solvable if the substrate line runs long enough. The metrology node is the closest thing this map has to a permanent dead end, but permanent is the wrong word. For a node that is funded, prioritized, and has a plausible domestic co-development path, unconfirmed bypass, timeline unknown, is the honest marking. That is a different status than no route imaginable, and the map should say so plainly. Reading the full map now, the glass substrate node is genuinely closed. BOE controls it, and that is not a small achievement. Borosilicate glass at the purity and dimensional stability required for advanced packaging is not a commodity, and getting there domestically matters. But controlling one node in a 10-node supply web is not the same as controlling the web. The 3 tool nodes I traced are not in the same position on the map. The metrology node is closest to production critical today. Without it, you cannot confirm the stack you're building. The optics integration node is closest to becoming critical tomorrow as co-packaged optics adoption accelerates in data center hardware. The laser drilling node sits between them in urgency. The constraint is real, but drilling at approximated specifications and iterating is more tractable than confirming buried alignment at throughput. Here is where I push back on my own earlier read. I initially framed optics integration as a distant future problem, something BOE would need to solve several technology generations from now. But if you trace the timeline of glass substrate adoption in the broader industry, data center interconnect demand is pulling that timeline forward. Companies building high-bandwidth switches and accelerator interconnects are staffing co-packaged optics programs now. If the technology matures on that schedule, the optics integration node may arrive at commercial relevance faster than the metrology bypass does. That asymmetry changes which choke point I would watch first. Not the laser, not even the metrology. Watch the optics coupling tool and whether any domestic vendor has a confirmed design win on a glass-based co-packaged optics line within the next few years. None of the 3 tool nodes has a confirmed domestic bypass. What I find most significant is not that China is behind on all 3. That is the obvious read. What matters is that the 3 nodes are in different bypass states. The web is not failing uniformly. It is failing at a specific sequence, and that sequence tells you which problem gets solved first and which one, when it does get solved, changes the shape of the whole map. The glass substrate is on the map. The through glass via is on the map. That single 10-micron hole, the junction the whole map converges on. BOE can drill it. What the map shows is that the tool confirming the hole is straight, the tool confirming the stack above it is aligned, and the tool coupling a photon through it are all still owned at the far end of a line that BOE does not control. The hole is there. The network around it is not closed. The node I would watch next is the metrology tool specifically. Whether a Chinese equipment vendor confirms volume shipments of a buried feature inspection tool to BOE's glass line in the next 2 years. If that line closes, the shape of this map changes in a way that matters more than any new substrate announcement. Which node do you think falls next, and what would be the signal that it has? Leave that in the comments. If you want to follow the map as the lines get redrawn, subscribe and turn on notifications. The next video traces the line from photoresist to the node no one is talking about yet.